This video is on fundamental theorems about groups. The theorems that we discuss in this video will apply to all groups, ranging from the familiar ones, like the integers under addition, to more obscure types of groups, like the power set under the symmetric difference operation. We've recently investigated the formal definition of a group, shown here, and we've seen quite a few examples of groups. Our next step then is to answer some questions about basic properties of groups. For example, this bullet here concerns an identity element in our group. Is that identity element unique? This bullet in the definition concerns inverses. Are these inverses unique? And also, when we're working with equations in groups, how is it that we can solve and manipulate those equations? We wish to answer those questions. Our first theorems are about uniqueness in groups. So we start with a group, G comma star. Because G is a group, the definition tells us that it must have an identity, and item 1 of our theorem claims that that identity must be unique. Also, if we're given an element x in G, we know from the definition of a group that x must have an inverse, and we claim that that inverse is also unique. Now there's some notation about inverses that we should be aware of. Typically, if we have an element x in the group, its inverse will be denoted by x raised to the minus 1 power. But sometimes, like when we're working in the group in the integers under addition, we are most typically used to denoting an inverse by a minus sign in front of the symbol. So here, minus x would denote the inverse of x in a group like the integers under addition. Okay, so let's go ahead and prove the theorem. So let's start with item 1. And we're going to start with two elements in G that are going to be identities. So then E1 I know is E1 star E2, and that's because E2 is an identity. Right? If I take anything times E2, I should wind up with what I started with. Now likewise, because E1 is an identity, anything times E1 should be the thing I start with. So that says that E1 star E2 should be equal to E2, and the upshot of this is that E1 and E2 must be the same. That is, if E1 and E2 are identities, then they must be the same thing. And so the identity element is unique in a group. Okay, for item 2, we're going to let B and C be inverses of x. So then, if we start with B, what can we do with it? Well, I know that that's the same as B times whatever the identity is, E. But E I can write as x times C. Right? And that's because C is an inverse of x, so x times C should be the identity. And now the associative property can kick in, right? I can write that as B times x times C. But B times x, remember, B is an inverse of x, so B times x is the identity. And the identity times C is just C. So the upshot is that B and C are equal, and therefore inverses are unique in a group. Our next theorem is about inverses in groups. So we let G comma star be a group, and we have X and Y being elements of G. The first item in our theorem tells us how to compute the inverse of a product in a group. So if you take X times Y inverse, that must be Y inverse times X inverse. The second part of our theorem essentially tells us that one-sided inverses are legitimate inverses. So in fact, down here, this B that you see really should be in item 2. So the point of item 2 is that one-sided inverses are legitimate inverses. So what do we mean by that? Well, in the very first sentence here, notice that we're told that X times Y is equal to E. And that means that it must also be true that Y times X is equal to E. And likewise, if we're given that Y times X is equal to E, then what we're claiming is that it's also true that X times Y is equal to E. Okay, so why don't we try to prove these theorems? Okay, so for item 1, let's start with our product, X times Y. And we're claiming that the inverse of X times Y is Y inverse times X inverse. So to test that, what I should do is take X times Y, multiply it by Y inverse times X inverse, and make sure that I get the identity. So luckily here the associative property comes to the rescue, and we can group this as X times Y times Y inverse times X inverse. And then the Y times Y inverse is the identity. So this is essentially just X times X inverse. And that simplifies to being the identity. And therefore, this product, Y inverse times X inverse, is the inverse of X times Y. You know, item 2 is a little bit more involved. So we're going to let G be the product Y times X. So here, by the way, we're going to verify the first sentence of item 2. We're going to show that if X times Y is equal to E, then Y is equal to X inverse. So we're going to start with this element G, which is Y times X. And we'll be done if we can show that G is equal to the identity. So I want you to note some things about G, or note something about G. So if we square G, right, that's just G times G. What is that? Well, that's going to be Y times X times Y times X and now again we use the associative property. This is Y times X times Y times X. But remember, X times Y is the identity. So this right here, this X times Y, that's the identity. And what that means is that this thing on the right-hand side of the equal sign simplifies to Y star X. But Y star X was equal to G. Okay? So what we have is that G times G in our group is equal to G. Now G must have an inverse in this group. So if we apply G inverse to both sides, That is, we multiply by G inverse on both sides. And then what do we get? Well, on the left, we would get just G, and on the right, we would get E. And that is what we wanted to show, right? We wanted to show that this y times x was equal to E, and we did manage to do that. The next theorems are about solving equations and cancellation. So again, we start with a group, G comma star. We have some elements A, B, and C that live in the group. Item 1 of our theorem tells us that if we start with a simple equation, A times X equals B, then that equation must have a unique solution in G, as does the equation X times A equals B. The next two parts of this theorem are referred to as cancellation theorems. So if I have A times B equaling A times C, then it makes sense that B should be equal to C. And the same in item 3, except we are multiplying by A on the right instead of on the left. So let's discuss this theorem. So for item 1, if we want to see why this is true, let's just start by solving the equation A times X equals B. Well, what do we need to do? Well, we would like to multiply by A inverse on both sides. So if we start with our equation A times X equals B, we know because G is a group that A has an inverse. So we get A inverse times A times X equals A inverse times B. And then because G is a group, we have the associative property. So we have A inverse times A times X equals A inverse times B. And then A inverse times A is the identity. And then we know that the identity leaves elements unchanged under multiplication. So that tells us that X is A inverse times B. And that's the only value that X can have. All right, so we feel this great satisfaction having solved an equation. So now let's move on to item 2, which is a cancellation law. Right, so let's suppose we've got A star B equaling A star C. Well, it's very much like item 1. The thing that we want to do is to multiply on the left by A inverse on both sides. And then, of course, we want to use the associative property. And then if there were more room in the slide, I would say that E times B is equal to E times C. And that would lead us to the fact that B is equal to C. And we're finished. Actually, item 3 is similar. If you want to, you can pause the video now and prove it for yourself. Okay, here we have an example that illustrates the first part of the theorem on the previous slide about solving equations in groups. So here we're looking at a specific group. In this case, it's the collection of invertible 2x2 matrices with real entries, and the operation is matrix multiplication. And here we have actually two equations to solve. And I guess the point of this example is that we need to be cognizant that order of multiplication can matter in a group, right? Not every group is abelian where A star B equals B star A all the time. So that's certainly true for matrix multiplication. I mean, at first blush, these equations might look identical to you, but in fact, we're going to see that they have different solutions. So let's start with this equation here. So if I want to solve for x, the proof on the previous slide told me that what I should do is multiply by the inverse of the matrix 5, 3, 3, 2, and that I need to multiply on the left side everywhere by that inverse. If I do that, I'll isolate x on one side. On the right, I'm going to wind up with 5, 3, 3, 2 inverse times 1, 2, 0, 3. Now the inverse of the matrix 5, 3, 3, 2 is 2 minus 3 minus 3, 5 times 1, 2, 0, 3. And let's see what that gives us. Well, I should get a 2 up here. 4 minus 9 would be minus 5, I guess. You all can check me that my arithmetic is okay. I get minus 3 times 1 plus 0. So that should be a minus 3 there. And then finally a minus 6 plus 15. That should be 9. So anyway, you all should check. Okay, so this is the solution to the first equation. Okay, so we'll label that 1 for the first equation. Now for the second equation, it's essentially the same process, but here we want to multiply by the inverse of 5, 3, 3, 2 on the right everywhere. If we do that, we isolate x on the left side, and on the right side, we have the matrix 1, 2, 0, 3 times 5, 3, 3, 2 inverse. But that's just 1, 2, 0, 3 times the matrix, what is it, 2 minus 3 minus 3, 5. And now let's see what we wind up with as a result. So I get 1 times 2, which is 2, minus 6, which should be minus 4. And already we can see that the answer is going to be different than the answer for the first equation. So we'll call this equation 2. Okay, so what other entries do we get? We get a minus 3 and a 10, which should be 7. So again, you should check to make sure I'm not screwing this up. Down in the lower left, we should get a minus 9. And in the lower right, we should get a 15. Okay, so the main thing to notice is that these two matrices here, these two answers that we get are different. And it's because the order of multiplication in this matrix group really does matter. So we finished this video with a theorem that slightly simplifies the properties we need to check to guarantee the set G with a binary operation is a group. So the theorem says, suppose we've got a set and we have an associative binary operation on that set. And let's also suppose we have a right identity. That is, we have an element E such that x star E equals x for all x in G. and that for each element in the group we have a right inverse. Namely, if we're given x, there exists a y, so that x times y is equal to this right identity. Then it turns out that this set with this binary operation is in fact a group. So what that would mean is that the existence of this right identity and these right inverses implies that this right identity is actually a two-sided identity, and that this right inverse is actually a legitimate two-sided inverse. So those are the things that we need to show in order to prove this theorem. Okay, so the first thing we're going to do is show that this right identity here is actually a two-sided identity. So we start with an element in our group, and we already know that x times e is equal to x. What we want to do now is show that e times x is equal to x. So there's a little bit of maneuvering that needs to be done before we can show that. So we know from the second bullet point that our special element x has a right inverse y. So I can pick a y in my group so that x times y equals e. And if x times y equals e, we can consider this expression, e times x quantity times y. Using the associative property, we can group the x and y together. But x times y is equal to e, which is my right identity. E times e is going to be e. But e, remember, is x times y. Okay, now how is that going to help us? Well, we know that this new element y also has a right inverse, which we'll call z, where y times z is the right identity e. So now what we want to do in the next series of equations is to show that, go back to our original goal, to show that e times x is actually equal to x. So first of all, notice that if we take e times x quantity times y, I know that e times x is x, so that means that e times x times y is x times y. So now if I multiply on the right on both sides of this equation by z, and I use the associative property, I wind up with this equation. But remember that y times z is the identity, or this right identity, so that leads to this equation. But now remember that e is a right identity, so this tells me that e times x is equal to x. And that was what we wanted to show. So we've shown now that this right identity is actually a two-sided identity. So we continue to address this same theorem. On the previous slide, we showed that this right-sided identity is actually a two-sided identity. And now we want to do the same thing with inverses. If we start with an element x in G, and it has a right inverse y, we want to show that y is actually a left inverse also. So that is, we know that x times y is equal to e, and what we want to show is that y times x is equal to e. So the method of procedure is a lot like what it was on the previous slide. Notice that if we take y times x times y and we use the associative property to move the parentheses, we get that y times x times y is just equal to y. Now, y must have a right inverse in G by the second bullet point, so we'll call that thing z. So we know that y times z is equal to e. So in the previous step, we showed that y times x quantity times y was equal to y. If we now take that equation and we multiply both sides by z, we wind up with this new equation where we have applied the associative property to group the y and the z together on the left side, but y times z is equal to e. And so if we apply that fact, we wind up with this equation, but e is an identity, so y times e is just y times x. So we wind up having showed that y times x is the identity, and you might recall that that's exactly what our goal was.